everybody, the purpose of this video is to go over the second part of section 10.1 where we will be talking about completing the square. Now in our last lesson we talked about using the square root method, and the square root method took advantage of the fact that our quadratics were expressed in terms of perfect squares. In other words, they either looked like this or they looked like this. And these are what we call perfect squares. Now the general form of a perfect square we can write as the quantity x plus b over 2 squared, and if we expanded that we would have something that looks like this. It'll be x squared plus bx plus the quantity b over 2, that entire thing squared. And of course then the other perfect square is when we have x minus b over 2 squared, and that has the exact same structure except for the fact that we have a minus sign instead of a plus sign. Now today we are going to talk about completing the square. And the question that we're going to be answering is, well, what do we do if we actually have something that looks like this, which by the way is not a perfect square? Well, what we're going to do is we are going to make it a perfect square. And the process of making it a perfect square is what we call completing the square. And how can we do this? Well, just notice that if we added 3 squared, which happens to be equal to 9 to both sides, we will have x squared plus 6x plus 3 squared, which actually is the expanded version of a perfect square. It's the expanded version of x plus 3, the entire thing squared. And indeed, if you actually multiplied this out, you would get x squared plus 6x plus 3 squared, which would be 9. Okay, well remember, if you're going to add 3 squared to one side of the equation, we have to add it to the other side of the equation as well, which is why we have the 9 here and the 3 squared there. They're both the same. And as a consequence, when we are done, we actually have that y, which is equal to 6x, which is equal to x squared plus 6x, is also equal to the quantity x plus 3 squared minus 9. These are actually the exact same quadratic equation. This is in standard form. This is what we call vertex form. And once we've written it in this form, we can go ahead and finish. We can actually go ahead and solve it for we can actually find solutions for it. And of course, the solution for the equation is whenever, or those values of x for which y is equal to 0. So here we set y equal to 0. And here's the equation in standard form. Here it is in vertex form. And then we can go ahead and use the square root method to solve this. First, we can actually get the perfect square on one side, this on the other side. We can take the square root of both sides, and we will have that x plus 3 is equal to plus or minus 3. When you solve for x, you will find that your two solutions are 0 or negative 6. And that pretty much is what completing the square is all about. It is trying to find that value that you need to add to both sides of the equation to turn one of the two sides into a perfect square. And we actually have a procedure that does it. And we're going to use this procedure against this quadratic equation right here. And the first step is to divide the equation by the leading coefficient. Here the leading coefficient is 3, so we're going to divide the entire equation by 3, and if we do, we will have x squared plus 4x minus 3 is equal to 0. Next, we want to move the constant term to the other side of the equation. And of course, we can do that by adding 3 to both sides of the equation. And if we do, we will have x squared plus 4x is equal to 3. And this is where we actually complete the square. We actually want to find the constant, that number that completes the square. What will that number be? Well, it will be the linear term divided by 2, which in this case will give us 2. And then we're going to square it. We're going to write that symbolically here as 2 squared, but we're going to evaluate it here and just write down what 2 squared is, which is 4. Now this right here is a perfect square. This can be written as x plus 2, the entire thing squared. And that will be equal to 3 plus 4 or 7. Which is exactly what we do in step 4. We write this side as a perfect square, and then we evaluate the right-hand side. Once we've done this, then we basically once we've done this, then we can use the stuff that we learned in section 10.1, or 10.1a to actually solve the equation. We can take the square root of both sides, which is what we've done here. We can go ahead and solve for x, and our two solutions will be x is equal to minus 2 plus root 7, and x is equal to minus 2 minus root 7. Okay, so that is our procedure for completing the square, and we are going to try that for these 4 problems. And we're going to do these problems in Notebook. Now remember, step 1 is to divide everything by the leading coefficient, which in this case is 3. So we're going to divide by 3 here, divide by 3 here, actually negative 3, and negative 3 here. And that will give me x squared plus 2x minus 5 is equal to 0. Now notice that this cannot be factored because there are no factors of 5. There's only 2, 1 and 5, that can sum to positive 2. Or no factors of negative 5 that can sum to positive 2. So this cannot be factored. Step number 2 is to move the constant term to the other side. We can do that by adding 5 to both sides of the equation, and that will give us x squared minus 2x, plus 2x is equal to 5. Now step 3 is where we actually complete the square, and we are going to do this by taking our linear term, which is 2, dividing it by 1, and then dividing it by 2, which will give us 1, and then squaring it and adding that to both sides. Well, 1 squared is just 1, but we're going to write it as 1 squared here. And of course, we're going to write it as just simply 1 here because 1 squared is 1. Now, this is a perfect square. And step 4 is to rewrite this as its perfect square, which would be x plus 1 squared. And please realize that if you actually expanded this, you would get x squared plus 2x plus 1. And that is going to be equal to 5 plus 1, or 6. Once we get it to this point, we can go ahead and use the square root method to solve this problem. We can take the square root of both sides. And if we do, we will have that x plus 1 is equal to plus or minus the square root of 6. We can basically isolate the 1 by subtracting 1 from both sides, isolate the x by subtracting the 1 from both sides, and that will give us that x is equal to negative 1 plus or minus the square root of 6. And our two solutions will be x1 is equal to negative 1 plus root 6, and that the other one is x2, which is going to be equal to negative 1 minus the square root of 6. And that's how we do step 1. Okay, as far as step 2 is concerned, we're going to do the exact same thing. We want the leading coefficient to be 1, so we're going to divide everything by the leading coefficient here, which is negative 1. This actually implies, the negative sign in front of the x implies a leading coefficient of negative 1. So we're going to divide every single term by negative 1, which is the same as changing the sign on every single term. And if I do, I will have x squared plus 10x plus 24 is equal to 0. Now, many of you might realize that this factors, and this actually does indeed factor to x plus 6 times x plus 4. And that kind of tells us that our solutions should be x is equal to negative 6 and x is equal to negative 4. But let's go ahead and complete the square and see if we can get the exact same thing. So we've done step 1. Here's step 1. Step 2 is, for step 2, we want to bring the constant term to the other side. And that will give us x squared plus 10x, notice how I give myself lots of space there, is equal to negative 24. And now for step 3, when we want to complete the square, and we will do that by taking our linear term, which is 10, dividing it by 2, which will give us 5, and then adding 5 squared to both sides of the equation. Here we're going to add it symbolically, 5 squared, and here we're going to add the evaluated version of that, which will be 25. Okay, once again, this is a perfect square. This can be written as x plus 5, the entire thing squared. And that will be equal to negative 24 plus 25, which is equal to 1. And notice that this right here is a perfect square. That actually happens to happen. If the equation is factorable, you will find that after you've completed the square, you'll find that the constant term will always be a perfect square. But nonetheless, we can go ahead and take the square root of both sides. So here we go. Square root here, and when we do, we will have that x plus 5, actually be minus 4, is equal to plus or minus 1. And then solving for x, we will have x is equal to negative 5 plus or minus 1, which will give us x is equal to negative 6, or x is equal to negative 4, which is exactly the same solutions we would have got had we factored. And this brings us to the third one. And here we have x squared equals 8x plus 25. First thing we want to do is put this in standard form. And that would be x squared minus 8x minus 25 is equal to 0. Now step 1 is to divide the entire equation by the leading coefficient. Since the leading coefficient is 1, we don't need to do that. We can go straight to step 2, which is to move the constant term to the other side. And that will give us x squared minus 8x is equal to 25. Now step 3, we want to complete the square. We will do that by taking 8, dividing it by 2 to get 4, and then adding 4 squared to both sides of the equation. So that will be a plus 4 squared here symbolically, and then plus 16 here. Okay, so once again, this is a perfect square. We can rewrite this as x minus, this time, since we have a minus sign in front of the linear term, 4, the entire thing squared, and that will be equal to 25 plus 16, or 41. Okay, now we get to this point, we are now back to where we can actually use our tools from section 10.1a, the square root method, to finish this up. And so we can take the square root of both sides. And if we do, we will have x minus 4 is equal to plus or minus the square root of 41. Okay, moving x over, we will have x is equal to 4 plus or minus root 41. And our two solutions will be x is equal to 4 plus root 41, and x is equal to 4 minus root 41. Root 41. Sorry about that. That should be a 1. There we go. And then finally we come to our last problem, which is x squared minus 2 is equal to 6x. Once again, we want to rewrite that in standard form. We can do that by subtracting 6x from both sides. These will cancel. We'll have x squared minus 6x minus 2 is equal to 0. Once again, we have a leading coefficient of 1, so we do not need to divide the equation by anything. So we can go to step 2, where we want to move 2 to the other side of the equation. And that will give us x squared minus 6x is equal to 2. And then once again, we can go ahead and we can complete the square. Actually, let me write this so I can actually go ahead and do that. Okay, once again, we have a 6. We want to divide that by 2. That will give us a 3. And then we want to write down 3 squared. We want to add 3 squared to both sides of the equation. So we will do that symbolically here. And we will do that with the evaluated version here. Okay, once again, this is a perfect square. We can write this as x minus 3, the entire thing squared, and that will be equal to 11. And now we can go and take the square root of both sides. Let's use rainbow ink this time, just for kicks. And if we do, we will have x plus 3, x minus 3, is equal to plus or minus the square root of 11. And then we can move 3 to the other side. That'll give us x is equal to 3 plus or minus root 11. And our two solutions will be x is equal to 3 plus the square root of 11, and x is equal to 3 minus the square root of 11. And these are all the examples that we have. I think given the fact that there's only 5 problems in Hawks, there's really no reason to do anything else on here. And that is all that I have for this particular video. If you have any questions, please feel free to contact me. This is Bob Boyle, signing off.